Welcome to this explainer. Today, we're going to do something actually kind of incredible. We are going to track the invisible rivers flowing right beneath our feet, and we're going to do it by completely demystifying the physics of groundwater flow. If you've ever wondered how scientists figure out exactly where water is moving hundreds of feet below solid ground, you are absolutely in the right place.
Here's our roadmap for today. We'll start by looking at the energy of groundwater, then mechanical energy components, simplifying the Bernoulli equation, understanding hydraulic head, and finally determining flow direction. Let's get right into it. Section 1. The energy of groundwater. To kick off our detective story, we really need to figure out the basic drive behind why water moves at all, right? Why isn't it just sitting still down there in the dark? Well, groundwater actually holds energy in three distinct forms: mechanical energy, thermal energy, and chemical energy. But the big overarching rule here, thanks to the laws of physics and thermodynamics, is that water always moves from regions of high energy to low energy. It's just nature's constant attempt to eliminate those energy differentials and find balance. Now, to keep our analysis clear today, we're going to assume a constant temperature, which lets us focus entirely on the mechanical energy side of things.
Which brings us to Section 2, mechanical energy components.
So what exactly makes up this mechanical energy that's physically pushing the water through the soil and rock? It neatly breaks down into three classic physics components. First up, we've got kinetic energy, which is the energy of movement, driven by the mass and velocity of the fluid. Second is gravitational potential energy, which is all about the water's elevation above a specific baseline or datum. And third is fluid pressure energy. When you combine those three components together and factor in the fluid's mass, density, and gravitational acceleration, you get the total mechanical energy equation. Now, I know it looks a bit heavy, but honestly, it's just a mathematical way of saying movement plus elevation plus pressure equals the total energy of our underground water. But watch what happens when we run a real-world data set through this equation. In this worked example, we've got standard gravity, a specific pressure, elevation, and fluid density. But pay close attention to step 1. The velocity of the water is so unbelievably tiny that the kinetic energy comes out to essentially 0. Meanwhile, the gravitational energy is 7.35 and the pressure is 1.47, giving us a total energy of roughly 8.82. You can really see a massive difference in the size of the components here. That kinetic energy is virtually non-existent compared to the other two. And that realization brings us right to Section 3, simplifying the Bernoulli equation. Seeing that kinetic energy is basically a big fat zero in our calculations leads us directly to the Bernoulli equation. Now, I know the Bernoulli equation can initially look pretty intimidating, but by dividing our total energy equation by fluid density, which gives us energy per unit mass, Bernoulli states that for a steady flow of a frictionless, incompressible fluid, the velocity head plus the elevation head plus the pressure head equals a constant. We call this constant the total hydraulic head. But here is your collective sigh of relief. As our source material points out, in groundwater, velocities are tiny. The water is moving so incredibly slowly as it just sort of creeps through tiny pores in the rock and dirt. Because of this, the velocity head is practically 0. So the absolute crucial takeaway here is that it can be safely ignored entirely. Just toss it out. And this brilliantly illustrates how we can simplify things. By crossing out that entire velocity head portion, the v squared over 2g part, we instantly transform a complex, heavy equation into a much simpler, highly practical two-part formula. Let's unpack that in Section 4, Understanding Hydraulic Head.
So, what are we left with after stripping away the velocity component? Well, we get this vital concept known as the total hydraulic head. Simply put, the total hydraulic head, represented by the letter H, is literally just the elevation of the water, the Z, plus the fluid pressure head, represented by HP. That's it. Elevation plus pressure. This right here is the absolute master key to understanding groundwater flow.
And measuring this hydraulic head is absolutely crucial, because underground environments are rarely uniform. The Earth is layered with all these different conductivities: K1, K2, K3, and entirely different thicknesses. The hydraulic gradient, which relies heavily on our hydraulic head calculations, applies uniquely to the flow through each of these individual horizontal layers. Without knowing the head, we really couldn't understand how water navigates this incredibly complex underground obstacle course. So how do we actually measure that pressure head and elevation head out in the real world? Well, hydrogeologists use this incredibly clever tool called a piezometer. It's essentially just a small diameter well with a short well screen at its lower end. When you sink this down into the aquifer, the water physically rises inside the tube in direct proportion to the total fluid energy at the open end down at the bottom. By measuring exactly how high that water rises, we are directly measuring the hydraulic head. Simple, but brilliant. Finally, let's put it all together in Section 5, determining flow direction.
Now we get to play detective and see how this builds into a real-world application. We're going to use data from our piezometers to figure out exactly which way our invisible groundwater river is actually flowing. Imagine we have a nest of piezometers installed at 3 distinct locations, A, B, and C. All 3 locations start at the exact same surface elevation of 225 meters above sea level. However, the piezometers are driven to different depths, and most importantly, they show different depths down to the water below the surface. 80 meters down for A, 77 meters for B, and 60 meters for C.
To figure out the flow direction, we have to solve this puzzle using some simple step-by-step deduction. We need the total hydraulic head for each point. The formula to get there is remarkably simple. You literally just take the surface elevation and subtract the depth down to the water. Doing this straightforward calculation for all 3 locations gives us our final hydraulic heads. For location A, 225 minus 80 gives us 145 meters. For B, it's 148 meters. And for location C, it comes out to 165 meters. Now remember our very first rule. Nature constantly attempts to eliminate energy differentials by moving water from high energy to low energy, or in our new terms, from the highest hydraulic head to the lowest head. Looking at our numbers, we've totally solved the mystery. We know for an absolute fact the water is flowing from location C at 165 meters down to B and finally to A at 145 meters. C to B to A. Mystery solved. Throughout this explainer, we've successfully stripped away the heavy math, completely dropped the velocity, and turned an abstract equation into a physical, workable map of the underground world. It truly is fascinating how a few simple measurements of elevation and pressure can reveal entire invisible rivers. Which leaves us with a pretty provocative thought. If we can perfectly map these hidden waterways using just basic principles of energy, what other incredible hidden forces are silently shaping the world beneath our feet, just waiting to be measured?